Surrounded by the semi-arid plains of Gujarat, the landscape abruptly gives way to a sprawling expanse of shallow water. To evaluate the sanctuary's viability, researchers deploy a mathematical model known as the Water Quality Index, or WQI. The WQI demonstrates that water quality is entirely relative. It is a mathematical construct determined by the specific physiological requirements of the intended end user. The assessment begins by capturing raw data. Researchers continuously monitor 22 distinct physiochemical parameters across 8 sampling sites within the wetland. These equations form the core of the WQI methodology. They take dozens of disparate concentration values and process them into a single, standardized metric. Instead of evaluating trace metals, dissolved gases, and macro salts in isolation, the formula aggregates them to produce a single scalar rating that defines the overall quality of the water. The crucial engine inside this calculation is relative weighting, represented as W sub I. The logic here is strict. The biological impact of a specific chemical is not uniform. A parameter that is lethal to an aquatic bird might be entirely harmless to a broadleaf crop. To see how this works, we set the target endems to human drinking water. The algorithm must prioritize the chemical parameters that pose the greatest biological risk to humans upon consumption. Parameters like pH, total dissolved solids, and sulfate receive the maximum assigned weight of 4, exerting dominant control over the final index. Conversely, parameters that are less critical for human digestion are assigned lower weights of 1 or 2, downgrading their mathematical influence to prevent data noise. The weighting system forces the index to view the water exclusively through the lens of human physiological tolerance. This map shows the spatial WQI results when the math is optimized for human consumption. The central sampling nodes indicate a moderate to moderately good classification, meaning the interior water is viable for human drinking after standard treatment. However, outright failures occur at the southern and western boundaries, marked here as Sites 7 and 8. These failures correlate to extreme levels of total dissolved solids. At Site 7, TDS concentrations reach 3,200 milligrams per liter, driven by silt deposits and accumulation of domestic wastewater. Next, we shift the algorithm's focus away from human consumption and target agricultural irrigation. This map tracks the results for agricultural viability. The sanctuary exhibits a much broader pass rate, dominated by good and moderately good classifications. This happens because the mathematical priorities have changed. For agriculture, the algorithm elevates the weight of the sodium absorption rate and electrical conductivity, as these factors govern soil permeability and crop yield. While human kidneys struggle with the high total dissolved solids found at the wetland's edges, the region's agricultural soils easily tolerate the specific ionic composition of this water. Shifting the formula a third time, we run the index purely for outdoor human bathing standards. Here, the governing parameters change again. Safe bathing relies heavily on maintaining strict pH levels and monitoring dissolved oxygen and biological oxygen demand to track microbial activity. This map shows the results for outdoor bathing. The wetland passes with near-universal good or moderately good classifications, requiring 0 prior treatment. When assessed entirely through an anthropocentric lens, the math indicates the wetland is a highly robust, multi-use freshwater resource. But adjusting the algorithm for the ecosystem's actual inhabitants, fish culture and wildlife propagation, reveals a severe paradox. This map shows the exact same water bodies. The classifications instantly shift to poor and unsuitable across nearly the entire sanctuary. The limiting factor for aquatic survival is dissolved oxygen. In this specific calculation, the assigned weight of dissolved oxygen jumps to the absolute maximum of 5. It mathematically overrides the rest of the chemical profile. The high oxygen requirement of native fish crashes against the overwhelming biological oxygen demand occurring in the water, as microbes rapidly consume oxygen to break down domestic and agricultural waste. To locate the exact sources of this pollution, researchers use principal component analysis. Using Varimax rotated R-mode factor analysis, the algorithm isolates the independent sources of variance controlling the wetland's chemistry. The variance-covariance matrix collapses the data into 4 primary factors responsible for the degradation. Principal component 1 alone accounts for over 36 It shows incredibly high loadings of total dissolved solids, sodium, potassium, bicarbonate, and chloride. This exact chemical signature traces back to point source sewage and industrial effluents entering the sanctuary from the northwest and south via the Brahmani and Bhogava rivers. Principal component 2 isolates a different signature, driven by high loadings of magnesium, phosphates, and extreme turbidity. This represents non-point source pollution. The phosphates point to heavy synthetic fertilizer application, while the turbidity indicates severe catchment soil erosion washing into the basin. The math proves that while the water passes human filters, the ecosystem is functionally dead for its native inhabitants. It is being suffocated by distinct agricultural and industrial vectors. This split screen compares the wetland's viability for human bathing versus aquatic life. The sanctuary's capacity to tolerate human extraction actively masks severe underlying ecological degradation. Addressing the point source pollution identified by the first principal component requires targeted interventions, specifically continuous mechanical dredging to remove the accumulated sludge from the river inlets. To address the second component, the surrounding catchment area requires an urgent transition to organic farming, cutting off the continuous influx of phosphates and magnesium. Further physical interventions, including structured buffer zone development and physical fencing, are necessary to restrict cattle grazing and localized dumping. Protecting a Ramsar site means recognizing that cleanliness cannot be defined by what humans can safely extract. It must be defined by the strict chemical baseline the native ecosystem requires to survive.